All this is Dr. Mobeen Sayed from drbeen.com. Welcome to one more show. A discussion that I wanted to do today was about the AstraZeneca and the DNA of our nucleus and the AstraZeneca going into the DNA. We've been talking about the messenger RNA-based vaccines a little more, for example, Moderna and Pfizer. We have talked about AstraZeneca as well in detail for how it is formed. The discussion about how that adenovirus actually works in our cell, excuse me. I was actually just holding Luffy before starting. I thought I'll show him to you. But as soon as I tried to click the button, he ran away and his hair gave me cough. Okay, so so what were we talking about? So AstraZeneca. So how does that adenovirus actually result in the production of the spike proteins? So because yesterday we were talking about the messenger RNA, I thought this was an interesting topic to bind it with that. So last 3-4 lectures are kind of a series of discussions that give us a good idea of how a vaccine works. So with this, let's start. Hopefully everyone is doing great and you are doing good. Great and good both. Let's start. So first of all, this is drbeen.com. Then this is the Bloomberg vaccine tracker. So far, more than 17.5 million shots have been administered worldwide. In the US, 6.25 million doses. So we are way behind. We thought that we would have administered 20 million doses by the end of the year or the end of the first week of January. So that clearly has not happened, and we are still stuck at a very low level. And if you see here, US has actually distributed 21 million doses to its various centers. But out of all of them, only 6 million doses have been administered. Kind of sad. Then on the global levels, total 17 million doses have been administered. US is leading, 6.2 million. Then China, 4.5 million. Then Israel, 1.5 or 1.6 million, which is really appreciable. And then UK, 1.4. UK should have been more, but anyways, UAE about 1 million and so on. So this is a quick look at the vaccine. Now the discussion is about the AstraZeneca. We know that AstraZeneca was approved for UK, emergency use authorization for UK. We also know now, so this is 6th January news, that AstraZeneca is also given approval or authorization in India and some other countries. We'll talk about it. The other links here are about how the viruses act as a vaccine. So this is a very good article here in News Medical Life Science that is about the adenovirus-based vaccines. And if I can just have you see this couple of things. This paragraph here, she is talking about the adenovirus that is used in AstraZeneca or other vaccines not being able to replicate. And we'll talk about that. And then finally, here is an interesting paragraph, and that is what other vaccines may be used or may be built with the adenovirus. And so there are HIV, Ebola, influenza virus, TB virus, and TB disease, and Plasmodium falciparum, although these are all in clinical trials. Then here is an interesting article about the AstraZeneca. This is a very interesting article about how adenoviruses replicate in our body or in our cells, and how do they end up in our nucleus, and then they work there. So I'll explain that today. And this is, again, some more references about the viruses, their DNAs, and then their entry into our nucleus. One more and one more. So with all of these references in our back pocket, let us start our discussion. So here is the AstraZeneca quickly. So the name is AZD1222 or AstraZeneca D1222. It is a modified chimpanzee virus. And why adenovirus? And why it is modified? It is modified to remove the replication capabilities. So once this virus is injected into our cell, all the genetic material from this virus that would allow it to increase in number is removed. So this virus cannot increase in number. So this is what is called replication deficient. So it is a replication deficient virus. And why use chimpanzee adenovirus? It's a common cold virus and not a human common cold virus. The reason for that is most of us have had common cold sometimes in our life. I think almost on a yearly basis. And because of that most of us have antibodies against human adenovirus in all of us. So if you make a vaccine that uses human adenovirus, and as soon as you administer that vaccine, our body is already trained against it, and it is going to destroy that vaccine even before it gets a chance to go and function. On the other hand, if it is a different animal's virus, then our body is not fully aware of it, and it would allow it to stay for a few seconds, or not few seconds, few days. And during that time, that virus can enter into our cell and deliver the DNA and make the spike proteins. So because chimpanzees adenovirus would allow us to not attack it and do its function of acting as a vehicle to bring the DNA into our cell, that is why we use this. So other vaccines that are in trials, HIV, as we just saw, Ebola, influenza, TB, and others. Approvals. UK gave the emergency use authorization on December 30th. India has given authorization. Argentina, Dominican Republic, El Salvador, Mexico, and Morocco. They have all approved AstraZeneca. And of course, India is the biggest customer at this time. So now is the big question. How does an adenovirus-based vaccine work? We know how does a messenger RNA-based vaccine works, and we know about the lipid nanoparticle and so on. So let's see, how does this work? So here is the virus itself, adenovirus. And what happens is, if I can show this diagram here as well, this diagram, if you see here on this virus, see those little red and green things? So on top of the virus, there is a coating of proteins, and you can call that sort of an envelope. Just like SARS-CoV-2 has an envelope as well. So here I have made that in green. So we have a virus particle which is coated in some proteins. This virus particle has these red spikes on it, just like SARS-CoV-2 has spikes. Here we don't call them spikes, we call them fibers. So these fibers connect with our cells and receptors. Just like spike protein on SARS-CoV-2 binds with our cell on ACE2, these spike proteins also bind with some other receptors on our cell. The result of that is that this adenovirus is brought into our cell inside a small vesicle. Vesicle will be a small piece of our cell membrane that becomes a pouch around this virus, and the virus is brought in the bubble made up of our cell membrane. So far, so good. We have a virus. This virus, especially in case of AstraZeneca, the vaccine, this virus is made in a lab, and it is made in HEK 293 cells. We have discussed this many, many times before. The exact production of this virus has been discussed before. The exact function has been discussed before. The comparison with other vaccines has been discussed before. So I'm not going there. I just want to make sure that we can understand, once the virus enters our cell, what's going to happen next. So here is the virus particle, connects with the receptor on our cells, and then it is brought in a bubble, which we call vesicle, which is made up of our cell membrane. This is just like if you look at my hands here. So imagine if this gray cloth here is the cell membrane, then when the virus is entering this cell membrane, it takes a piece of the cell membrane with it, and it is covered by that. So that is this structure here, that blue thing around it. Now, what we do is, and we have discussed this in the past as well, that when we bring something from outside, that is called phagocytosis or pinocytosis or endocytosis. When we bring something from outside, we then combine that phagocytic vesicle with the acidic vesicle that we have in our cell. You can say small stomachs are present in our cell. These tiny microscopic stomachs, they have lysosomal enzymes in them. Lysosomal enzyme simply means they have chemical substances that would digest and destroy whatever they come in contact with. So we fuse the viral particle vesicle with the lysosome together, which allows the lysosome to spill its guts, its acids, into this virus particle vesicle. When that happens, because these tiny stomachs they have acids in them, so what would happen is that as the acid appears in this vesicle, the pH drops. pH drop simply means acidity inside this cell increase, not cell, the vesicle increases. So far so good. We brought in the cell. So folks were complaining yesterday that I was going fast, so I'm kind of making sure that we go step by step. So the virus brought in a vesicle, then we fused with that vesicle the lysosomal vesicle, which is a small stomach of the cell, and there are millions of these stomachs inside the cell. They have acids in them. Those acids are brought into the vesicle. Now, the adenoviruses are very clever virus. If this was another virus, bringing in the stomach or the acids will actually destroy this thing. But adenoviruses, the common cold viruses, have changed themselves that when they get this acid, it allows them to become active. So imagine these viruses look like an orange, which has a skin on it. And imagine if you put acid on that orange, that would cause the skin to be removed and the fruit to come out. That is what these viruses have adapted themselves as. So when you try to destroy them, they actually become active with that. So what they do is, if you see here in this part, they remove, using those acids, they remove their coating and they remove the fibers that were attached to them. The remaining thing, this is called uncoating. They remove their coat. If I took my shirt off, that will be uncoating. So they remove their coat. And now what remains is the virus DNA and the proteins around that are called capsid. So very sharp virus. It used the acids to remove the outer layer. Now this inner layer that comes up, that is available, that can escape from this phagolysosome. So that is the clever thing about this virus. So virus can then break out of it. This is called the viral escape. Isn't that interesting? Other viruses don't do it. Some viruses do this. So when it escapes out here, so see this little red thing. Now this red thing has removed its coat. It has given up its fibers, and the capsid and the DNA has come out. Now in this DNA here, in this DNA is the genetic material for the spike protein. This is a virus whose DNA we have changed in our labs, that this virus cannot make more viruses, and all it contains in it are the genetic material for the enzymes to help replicate its or make messenger RNAs, and the messenger RNA or the DNA for the spike protein. So keep an eye on this guy now. The thing is that this guy here, it has to actually send its nuclear DNA, its DNA, not nuclear DNA, its DNA, which contains the DNA for the spike protein, in the nucleus of our cell. Because DNA can only be converted into a mRNA inside the nucleus. So that is this virus's challenge. So you may ask me a question over here, and that is, well, we had always heard that the spike protein is RNA. Why do we have a DNA of the spike protein? So in the lab, we manufacture the DNA pattern for the same RNA that makes spike protein. From this DNA, we will make RNA in the nucleus, and then we'll be back to normal. So let's see what happens. So again, so far, the virus is inside the cell. It has become uncoated. Now it has the DNA in it, and its job is to bring that DNA in our cell's nucleus, where it can use the DNA machinery that is inside the nucleus to make messenger RNA. That is the next step. So here is what it does. It needs to, we say docking, it needs to dock with our nucleus. So what happens is, in our cell, so if this was our cell, in our cells, we have thousands of tiny microtubules. You can think of them as small roadways. On these roadways, special proteins or special cars are running all the time, special cars. These cars, the trucks and the cars, these cars are called kinesins. Kinesin, sin means a protein. Kine is from kinetic. It's a kinetic protein. It runs, it functions, it walks. So here is this little kinesin protein. Imagine it is a car that is on this roadway. It has this virus capsid attached to it. It walks on this microtubular roadway. We call these roads as microtubules, and it brings the virus all the way to the nucleus. Isn't this interesting? So virus came in, it released its capsid, which has the DNA in it. Now the virus needs to bring its DNA in the nucleus. So our cell is going to help that we have roadways in the cell. These are microtubules. On the microtubules are small cars. These cars are called kinesins. Kinesins are going to pick up the virus itself and haul it to the nucleus. Kinesin's job is to move the cargo from one place to another place inside the cell. Okay, so once the virus has brought to the nuclear membrane, there are tiny pores in the nuclear membrane, which are called nuclear pores or nuclear pore complexes. Pore simply means a hole. And we have talked about nuclear pore complexes in the case of ivermectin as well, because remember, ivermectin blocks the SARS-CoV-2's cargo from going into the nucleus through these nuclear pores. So these are similar nuclear pores. But this virus here, the modified adenovirus, it does not need importin alpha and beta that was used by ivermectin. It can actually be brought in to the nucleus and attached to the nuclear pore by the kinesin. Once it is attached here, so if you see here the virus is now attached to this nuclear pore, and what virus does is that its outer coating, the capsid, is almost kind of disintegrating, and the nucleus that is present in it is injected through the nuclear pore into the nucleus of our cell. So now the spike protein DNA has been injected in the nucleus of our cell, where our remaining DNA is. Now what happens? What's next? From this DNA that has arrived in the nucleus, we now need to produce messenger RNA. That messenger RNA will then produce the spike proteins, as we have been seeing with the other vaccines in our previous days. So let's see how does that happen. So now imagine this huge structure is the virus DNA present in our DNA. I have not drawn our own DNA in here. So I shouldn't say virus DNA present in our DNA. That's wrong. It is virus DNA present in our nucleus, where our remaining DNA is present as well and doing its own function. Now that this DNA is in our nucleus, DNA has machinery or enzymes that can recognize a DNA and that can express a DNA, meaning they can open up that DNA as a recipe book, and then they can work on the instructions in there to help the cell produce some proteins. So imagine this whole part here, this whole thing is the viral DNA. It is present in our cell. This part here, as you can see, I have made it opened bigger. So this is called the gene expression. A part of the DNA has become opened by the machinery inside the DNA, inside the nucleus. And this was the original recipe. And then our machineries, our enzymes, make a copy of that recipe, the one in green. This copy is called messenger RNA. And we talked about in detail the structure of the messenger RNA yesterday. So imagine this messenger RNA is now formed in our nucleus by the enzymes that work on the DNA. This messenger RNA now needs to get out of the nucleus to go in the cytoplasm of the cell and work with our ribosomes to make proteins. Which proteins? Spike proteins. So what would happen is, if you see here from yesterday's talk, this is the actual recipe. On the recipe, we have a cap. On the other side, we have a poly A tail. Then we attach this whole thing to a machine, a small tractor, a small enzyme that is going to haul it outside of the nucleus. It is going to drag it out of the nucleus and bring it in the cytoplasm. So this is the cap binding complex. Cap binding complex. It is a small tractor machine or enzyme that is going to drag from the cap and drag the RNA out of the nucleus. So once the RNA has come out of the nucleus, then we saw yesterday that RNA will be then attached with the ribosomes that are present in our cytoplasm. These are those chefs who are going to look at the recipe and they're going to make proteins. So look what happened. How did this vaccine differ from mRNA vaccines? mRNA vaccines directly manufactured this thing and directly injected them, and it went into cytoplasm. So nucleus was bypassed. In AstraZeneca's case, it's a DNA type vaccine. So the adenovirus is acting as a vehicle to bring that DNA into our cell's nucleus, where that DNA is transcribed. That is a medical word we use. Transcription means making a messenger RNA from the DNA. So in this vaccine, instead of making messenger RNA in the labs, we have made DNA and we have given the duty of making messenger RNA to our cell's nucleus. So the DNA is brought in here. Over there, it is converted into messenger RNA. The remaining product is the same as the Moderna or Pfizer. So that messenger RNA comes out in the cytoplasm. In the cytoplasm, the ribosomes attach with it. They make proteins. These proteins are the spike proteins. Those spike proteins, as we talked 3 days ago, they will be fed. They will be fed into endosomes. Endosomes are small threshing machines, small threshers. They're going to chop and break the spike protein into tiny pieces. Those pieces will be loaded up on major histocompatibility complex 1 or 2 or MHC1 or 2, which will then present that piece of the spike protein on the cell's surface. Beautiful mechanism. So if you see here, virus brought in the DNA. That DNA eventually ended up in our nucleus. That DNA was converted into messenger RNA. That messenger RNA came out into the cytoplasm of our cell, the same cell. Cytoplasm converted that into a spike protein. Spike protein was fed into a thresher called endosome. Endosome breaks down the spike protein into smaller pieces. Those smaller pieces are loaded. Those are loaded on MIC complexes and are presented on the cell surface. Once they are presented on the cell surface, then the effector action occurs. And we have seen this many times, that it is possible that the natural killer cell or cytotoxic T cell that is attached here would become active, or it is possible that a T helper cell would become active, which would then cause B cell and cytotoxic T cells to become active. We have talked about it many times. So I just simply said here the effect would occur. And the effect could be cell killing by cytotoxic T cell, and a broken cell would activate the immune system, or effect could be directly activating the immune system if the cell here is the T helper cell. So if it is a CD4 T helper cell, then B cell and CD8 T cells would become active. If it is a CD8 cell, then that would directly kill the cell that is presenting the vaccine. And I'm being brief here with this part because we have done like 20 talks about that. So this is how this vaccine works. Eventually there is spike protein production. Eventually there is presentation of the pieces of the spike protein on the cell surfaces. And eventually there is the production of the immune system response. That is how this vaccine works. There is a slight difference from Moderna and from Pfizer. This is the talk for today. Let's see if there are any comments or questions about this mechanism. Okay, so there is a question. Kat Bach says, this is a different subject, but as a not medical professional, my question is, in the admission of a patient having cytokine storm, could a dose of chemotherapy drug not be given to stop the storm? Depends what is the drug and what is the storm's reason. If the storm is because of macrophage activation syndrome, then we have to give something to suppress the macrophages. May that be chemotherapy, or may that be direct suppressors of macrophages or interleukin suppressors. So it really depends what is the abnormality, and that needs to be targeted. Arun question: can free DNA chunks be transcripted? DNA vaccine needs a lot of process. Does it mean efficacy is less for DNA vaccine? So the second part of your question, DNA vaccines, as you can see, its efficacy is actually less. In one dose, it said 62%. In the half dose, full dose, they said 90%. Overall, 70%. So I am just confused about their efficacy drama. I'm sorry, I'm not convinced, and I'm not super excited about AstraZeneca. Having said that, ideally, it should not make a difference. It's just that the virus DNA is going through our nucleus and then creating messenger RNA. And in the case of Moderna and Pfizer, we're making the messenger RNA in the labs. Now, the first part of your question, can free DNA chunks be transcripted? They can be transcripted. So if I go here to the transcription part, these can be transcripted, but they also need to be in the right format. Just like messenger RNA has to have a cap, a poly A tail, a 3 UTR segment, a 5 UTR segment, a stop codon, a start codon. We discussed all of those yesterday. Similarly, if you want a piece of DNA to be transcribed as well inside the nucleus, it also needs to have all the formalities around it to become possible to be transcribed. So for that, the vaccine makers make the DNA in such way that all those formalities are present and the enzymes can recognize that DNA to be a valid DNA to transcribe. Any DNA fragment willy-nilly cannot just enter the nucleus and get transcribed. So you have to prepare the DNA with all the bells and whistles attached to it, which signal our enzymes in the nucleus to say, please work on this thing. Karen says, how long does COVID immunity last? So we know that COVID immunity lasts for 8 months for at least from the studies. From the past SARS-CoV-1 or MERS-CoV, we know that it can last for up to 2 to 3 years for antibody-based immunity, and cytotoxic-based immunity can go on for decades. So ideally, these vaccines, if they can create decent immunity, it should go on for years, but data is not present. So then there's a question from Brown Hilda. Is there any chance that the vaccine's recombinant DNA brought into the nucleus can interact with the cell's DNA? Okay, good question. And Barbara, thank you very much for the super chat. So Brown Hilda, good question. In theory, it is possible that viruses that are DNA virus that bring their DNA in our nucleus can accidentally impact our nuclear DNA as well. I'll show it to you here. So if you see here, it is possible. See this oncogenesis? This is the crondon.com, and these are the links are present in the description. So if you see here, some adenovirus serotypes are capable of inducing tumor growth. So some of these can actually cause tumor growth, but the reason is not that they impact our DNA. Reason is they bring in enzymes that can cause acceleration of DNA replication, because that is the job of a virus. In the case of AstraZeneca vaccine, those enzymes are removed. For example, if you see here, this involves the genes E1A, E1B, and sometimes E4. These are enzyme names that help open up a gene and express it and make messenger RNA with it. In case of AstraZeneca's vaccine or adenovirus vaccines, these genes are removed. So the DNA that is brought into our nucleus is not capable of accelerating the replication. It's not capable of replicating at all. So because of that, it is a very difficult possibility for the DNA vaccine to induce tumor growth or to become integrated into our DNA. Integration into the DNA only occurs when our DNA is also opening and closing fast, and those enzymes are not present in this virus. And this is exactly what we mean by replication deficient. Very good question. So Anurag says, which vaccine is better? We have done this discussion multiple times before. So I think the better vaccine is really lots of factors. If you look at the efficacy, Moderna and Pfizer have 95% efficacy. AstraZeneca's efficacy in one case is to be 62%, in another case was 90%, then they averaged them and said 70%. So that I'm not comfortable with that idea. But anyways, that's their efficacy. Moderna and Pfizer are not made in clones of the fetal tissue. So that is another debatable point for some folks. AstraZeneca is manufactured in HEK293 cells that were from the aborted that are copies of the aborted fetal kidney cells from 1972. So there are some folks who do not like that idea. So there are multiple ways to look at what is better. I think it's, other than the technical part, there are some other parts as well. Then multiple doses. For example, there are some vaccines that only need one dose. I would prefer that over those that need multiple doses. So really it depends on many factors to decide what is better for one person. Shahida says, will you please tell what is meant by positive sense RNA? Then there should be a negative sense RNA. Yes. So very quickly, and this, Shahida, I had talked about this right in the beginning about 6 months ago. What happens is, in our cell, this is the, let's say this is our ribosome, right? So this is our cute little ribosome. Its function is to work with the messenger RNA and translate that into a protein, correct? Now, messenger RNA, so let's say this is a messenger RNA. It can be ready from 5' to 3' there is a signal attached to RNA that tells this ribosome to pick it up from here and work on it. Now, some RNAs have that signal attached to the wrong side. So our ribosome our ribosome cannot pick them up and work with them. I can say it in one more way. There are, let's say if we have adenine here, then we know that we would have thymine on the other side. I'm just making up the complements. In some cases, this complement can work with this ribosome, but the other complement cannot. So if this complement cannot work with the ribosome, then we'll say this is a negative sense RNA. It cannot work directly with the ribosome. We have to first convert that into a copy, which will then be able to be inserted in the ribosome, and that would be called positive sense. So if I make it even more simple, I would simply say, if there is a piece of RNA that can be directly injected into a ribosome and it would start working there, then it is called positive sense. On the other hand, if there is a piece of RNA that cannot attach to the ribosome before you make a reverse copy of it, then that RNA is called negative sense. SARS-CoV-2 is a positive sense RNA. That means when it arrives into our cell, its RNA directly attaches with our ribosome and starts functioning. It doesn't need its reverse to be made. Some viruses have negative sense RNA. They need to be first reverse duplicated, then they can be worked on. Hope that answers that question. So there's a question by Professor Mulazim Hussain Bukhari Sahab, who is my teacher as well. What about the CanSino being trialed in Pakistan? Either these are synthesized in the same way like AstraZeneca. So CanSino is also adenovirus-based vaccine. The only difference with AstraZeneca is that the CanSino has one dose only instead of 2 doses. Secondly, for CanSino, we have no data. So without data, we actually cannot even say what is the efficacy of it. Interestingly, China has been able to influence countries to start using it even without data. So that is just fun. Anurag says, so what happens to the remaining DNA of the adenovirus inside the nucleus? Does it have any possibility of affecting our cell in a harmful way in future? Very good question. And just like yesterday, we talked about what happens to messenger RNA. And we talked that as soon as the RNA has done its function, our enzymes, the ribonucleases, exonuclease and endonuclease, they attack it and shred it and eat it away and digest it and destroy it. That is the same case for these kind of DNA pieces. These DNA pieces can stick in there for some time, but eventually they would be decayed and destroyed. Yes, I have been in touch with Dr. Drew almost on a daily basis. I hope he recovers fast. So that is correct, Brownhilda. Whenever you would hear the word adenovirus, that would mean that they are manufactured in some cell line. That may be HEK or that may be PR or other lines, but they are going to be some cell lines. You are welcome. You are in the shower. So who is in the shower? Oh, so the that little ribosome. So Denise is in the shower. Okay, it is bad that cool. So this is the Ken says, I would love to see the process of making this stuff and how they can churn this out in mass, how we can make exact copies of the vaccine and know the exact concentration of material. So Ken, if you go to AstraZeneca's site, they actually have a video for how they make it. I have done this discussion as well, and it is actually possible for what they're doing. Okay, so looks like this is what we have for today. Okay, so Akhil has a question. So is there a signal from the nucleus with the virus DNA that specifically attracts the vaccine particles to it? So the virus has the structure that makes it attached to kinesins. Kinesins' function is to bring whatever cargo you give them to the nucleus pore. Once the virus attaches to the nucleus pore, by that time it is already kind of disintegrating, and it injects the DNA into the nucleus. So there is nothing, no brain in there. This all is just selection of the virus and the proteins in a way that these assembly lines function this way. Cool. So thank you very much. There's a question, one more question here. Melanie Goodman. What other DNA components are present in addition to the spike protein transcript? So mostly the DNA decorations that allow the DNA to look like a complete DNA for our enzymes to bind with it and work with it. But all those replication enzymes from the DNA have been removed because we don't want this DNA to come into our nucleus and make more adenoviruses. We just want the DNA to make spike protein. So the DNA is really trimmed down to the point of making spike proteins. Cool. So I got a trophy today. Thank you very much, TD. Muhammad says, what about antibody neutralization memory? So with the spike protein that we just talked about, that would then create the immune system's response, which would create memory cells as well. So if you please look at my previous talks, I have discussed this part in detail. So much in the pipeline, it gets confusing. Not for our cells machinery. Cool. So Ruby's Red says, can you please do a show on the convalescent plasma and mutagenesis enhancement? Sure, we can talk about that. So cool beans, this is the discussion for today. There is one more question from Nabu. So the question is, does our DNA play any role in transcribing the viral DNA? Our DNA, no. Our machinery in the nucleus, yes. So the machinery, good question, Nabu. In this DNA, so let's say this is a cell and this is a DNA. Inside the DNA, there are machineries or enzymes that know how to work on a DNA, open it up. Imagine this is a master copy of recipes, and there are the keepers of the recipe. And if you want a page's copy, let's say you want to make fried chicken, and you send them a message to say, hey guys, I do not know how to make fried chicken. Can you look at the DNA and look at the recipe for that and send it to me? The message would go to these guys, these enzymes. They know in the DNA where is the recipe for the fried chicken. They would go and open up that part of the DNA, and then they would make a copy of it, which is called the messenger RNA. Then they would send that copy outside that can be fed into the ribosomes, which are the chefs, and they would then make those proteins. So the same enzymes that are present in our nucleus will help transcribe the viral DNA as well. Some actual viruses bring in their own enzymes too. They carry them with them, and they say, you know what, F it, I do not need your nuclear enzymes. I'm going to bring in my own enzymes. They would help me do my own transcription, and I would make my own assembly. Messenger RNA would go out, that would create proteins. Those proteins would then get back into the cell. Over there, the new viruses are made, and it's not the cell, the nucleus, and then the virus comes out. So there are many ways viruses do it. In the case of the spike protein, AstraZeneca, our nuclear enzymes will help as well. They have their own enzyme too to start the transcription, but our enzymes would work too. Cool. I just saw Margaret's message. So thank you, Dr. Bean, and wishing all cool beans an awesome evening, day, morning, and good night. Thank you very much. Doing good, bit fed up. What happened 1x2? I hope you're okay. Yes, great question and hopefully great answer as well. Cool. So this is it for today. Thank you very much. Please like, subscribe, and share. There is a link in the description for coffee. So if you would like to buy me a coffee, there is a link there. If you would just like to support the channel as well, there is another link in the description as well. So thank you. And I see a question from 1x2. So 1x2, you are a little fed up, so I'm going to answer your question. If the vaccine misses the deltoid muscle, is it less effective? No. It's just that the thickness of the deltoid muscle is such that it would irritate us less, it would create immune response correctly, it would not bother us too much. And it is kind of a harmless place, although they've caused a couple of people's shoulder damage by incorrectly injecting, but that is an injection, the person who is injecting, their fault, not vaccines. So shoulder, vaccines used to be in the buttocks, but they have found out that deltoid muscle has a decent thickness and the tissue in there that helps for the function. So no, if it misses the deltoid muscle, other muscles would do the same thing. The only thing is, we would not want an intramuscular vaccine to be given intravenous. So it should not go into blood. It should just go into the muscle. It can go in buttocks, for example. Thigh muscle is thicker, absolutely. That can be used as well. So a muscle. Absolutely, Marwans. Lots of coffees. So there's a question from Nicholas. Dr. Bean, have you talked about sauna use, heat shock proteins? No, not yet. It is a good point. It's a good topic. I have not discussed it yet. France, Denise, try dry brushing for lymphatic system. Easy to add to the other 4 things you do. Okay, so there is a totally separate discussion going on as well. All right, cool. So thank you very much once more, and see you tomorrow. Please like, subscribe, and share. Link for coffees in the description and link for support in the description as well. Tomorrow we'll have open forum. If you go to Twitter, you can actually write questions that we can answer. My Twitter handle is here at Dr. Bean _medical. Thank you very much. See you tomorrow.